So our next talk is about enhancing threshold group action signature schemes, and it will be given by Michelle. Okay. So let's welcome Michelle.
Okay. So I will talk about threshold signature scheme from group action and how to enhance them with more secure secret sharing and with some additional security capability. So, okay, this is what a threshold signature is. We have a talk 2 days ago, so it will be pretty quick. It's basically a version where you are doing a digital signature, but you have like your secret key shared with multiple people, and they all need to agree, or at least a threshold of them need to agree to sign the message. So it's a multi-party protocol that simulates a normal signature. Differently from the other talk, we are not going to do UC model stuff. What we are going to do is a standard unforgeability property that mimic the one for normal signatures. So we have like a standard idea that the adversary should not be able to sign even if it corrupts at most T-1 at least at most T-1 player. This definition will be modified later, but for now we will deal with it. So, okay, first of all, so what is a group action? A group action is simply a function between a group and a set to the set itself. We usually use this notation with the star symbol or similar symbol. And the main property we ask is that the function behave nicely with the group structure. So like the neutral element of the group like fix the set element, and there is this nice composition way that like is compatible with the group operation. I will use multiplicative operation, but of course it's the same if you want to have additive one. And we can ask many properties. I summarized the main one in the top half, but we will not use it because our approach aims to be as black box as possible. This is a big limitation, of course, but it's also a good way to generalize results. The main property we ask are the second one that are like the basis for doing something. As we want the group action to be efficiently evaluable, this is not an easy task. Like there are many group actions that have some limitation in this sense. And we want to be one way, so hard to invert, so that we can use this assumption, this like hardness problem, that is the group action inverse problem that basically states, okay, you have X and Y. You know that there is a group element such that X is equal to G times Y. The goal is to find G. This is the general problem. There are many group actions that have this problem. It's not always a problem in the post-quantum setting. There are many group actions that are safe in the post-quantum setting, but many that are not. So, for example, the most famous group action is the discrete logarithm. This is, of course, not safe in the post-quantum setting. And in the post-quantum setting, the most famous one are this one. This is not an exhaustive list. Like there are probably many other. But this is just to give an idea and to provide the fact that maybe you already stumble in some of them, but they usually have a different name. So like, for example, if you read Les and Matt's paper, they call them like linear code equivalence or matrix code equivalence, and they are indeed group action. And like the linear code equivalence problem is a special instance of GAIP, or we have the hard homogeneous space that is usually the name that they are using for isogenies, or true linear form based, or like lattice isomorphism that is the basis of falafel, that is ring signature based on lattices. So like there are multiple ways to call the group action inverse problem, but the substance is always the same. You have a set X and Y, and you need to find the group element that link them. And okay, so we start with the basic protocol. So how can we build an identification protocol for group action? This is the same structure that many signatures have, for example, LESS, but also many others. So our public key is X and X prime, and the secret key is G, the group action that link them. We want to prove the knowledge of G, and we follow this standard structure. So the prover like pick a random G tilde, apply it to X, and then we challenge, like it reveals the two diagonal line. One is for challenge 0, we're revealing G tilde. In challenge 1, we are like revealing the dotted diagonal line. So that like this diagram commute by group properties, basically, is pretty quick to see that there's honest verifier zero knowledge and special soundness. Like the special soundness is like you follow the line and you will get there. For honest verifier zero knowledge, you can notice that when the challenge is 0, you're not using your private key, so of course it's simulable. When the challenge is 1, what you do is, well, instead of drawing the picture like correctly, I started applying G tilde to X prime, so of course I can answer to the dotted line. Of course, I lose the ability to answer to the other one, but this is not relevant. Okay, so the first step is to obtain a full threshold. So when the n is equal to t, so I require all the participants to participate in the signature generation. And the idea is pretty simple. I split the secret key in multiple group elements such that the product is the secret key. So this is the structure. So how the key generation work? Well, simply we start from x0. The first player pick g1, compute g1 star x0 and reach x1, give x1 to the second player, and so on until we reach xn. This is pretty cumbersome. It requires a communication round, and so it seems bad, but it turns out that it's optimal. There was a paper from Emanuele Giunta that was like more or less developed in the same time we developed our first version that showed that computing a group action in a black box way and in a multi-party setting require communication cost that is proportional to the number of players. This is exactly what we have. So unfortunately, you cannot do any better unless you like want to add some hypothesis about how you can act on the group. So like using the real group action and not the black box one. So how we can compute the signature then? Well, to compute the commitment to x tilde n, like we follow the same approach for generating the key. So every player pick g tilde I and apply sequentially one after the other. When we need to like answer, so for challenge 0, well, the challenge 0 is pretty easy. Every player can simply reveal the tilde element and then you do the whole product. There is nothing like unsafe to do that, so fine. It's a little bit more cumbersome to reveal the final dotted line, but the idea is like to exploit this structure that are like triangle that are growing bigger. So the first player can compute the first diagonal line, dotted line, by doing g tilde 1 times g1 to the -1. And then you can increase this line sequentially with the second player, apply on the left the g tilde 2, and on the right g2 to the -1, and then like keeping like applying. Remember, like the group is not commutative, so you must keep the order correctly and like do sequentially, but you reach the final line. And why this is secure? Well, intuitively, because what I'm doing is like multiple sequential instances of the base protocol, because you can always draw like every horizontal line can be like public key of the centralized protocol, and every instance is a new instance of the previous protocol. So this is more or less how the simulation works. Like you can simulate exactly as the base protocol to obtain a static secure protocol. Okay, how can we pass to a generic threshold? Well, we do not have any property on the group. And so, for example, it's not a field, so we don't have two operation. We cannot use Shamir secret sharing because like it's not a ring even. So like you can invert stuff and add stuff. You cannot operate on a set element directly. Like if I give you two elliptic curve, you cannot like mesh together to find a new elliptic curve. Of course, you can only apply an action, and it's not even commutative, and so this is makes stuff more cumbersome. So the only, or at least our first idea was let's use replicated secret sharing. I will not talk about how you can obtain a replicated secret sharing. The only important part is the last one, that you have an exponentially large number of key that is namely n over t minus 1. That is then the threshold we are looking for. This is really bad for a performance standpoint, but will also be bad for like security standpoint, because now we are ready to tackle the adaptability, the adaptive security. So what is a threshold signature which is adaptive secure? Well, the idea is in the normal setting, we want that the adversary is able to corrupt people only at the beginning of the protocol. So before or after the key generation, depending on your setting, but this is not really important. But once you decide all the T-1 player he wanted to corrupt, then like the stuff is finished. So we start with simulating the signature query, simulating the random oracle, and so on, but no other corruption are allowed. And this, of course, simplify a lot the settings. In the adaptive security, the idea is, okay, the adversary can corrupt some player at the beginning whenever he wants, and then we can like start to simulate the signature query and so on, but the adversary can stop at any time, also in the middle of a signature query, whenever we want, basically, to corrupt more player. Of course, like the maximum number of players allowed to corrupt is still T-1, otherwise it will be trivial to produce a forgery. But the idea is that delaying the corruption can yield for another way to simulate, because you need to make your like all your messages consistent with future corruption. So you cannot simply rely, okay, I give you something random, you will never discover it, because at some point maybe you will need to prove that everything was made correctly by revealing your private data. So the first idea was to introduce this new hard problem that is a pretty natural extension of the group action inverse problem that is also, for example, used in the discrete logarithm setting. That is another one discrete logarithm we call chain group action because we have a sequential way. But the idea is like I have a sequence of group action and group action one after the other. I'm not asking the adversary to solve all of them, but I'm asking the adversary to solve at least one of them. And it can query our oracle to obtain all the other one. And this is like the same stuff you can do in the discrete logarithm stuff. If you have, for example, read the paper Sparkle, they use a very similar idea for proving the adaptive security of Schnorr protocol. So anyway, this clearly is the same way of the discrete logarithm. Have a security loss that is proportional to the number of query, of course. Like I can run a GAIP adversary to these instances and parallel time, one of each single instances, and I win if at least one of them wins. So clearly I'm multiplying my success probability by a factor of n. This is like pretty obvious, of course. But anyway, posing this stuff for a moment, the idea is that if I apply, if I use this kind of notion, and I modify a little bit my signature scheme, I can obtain pretty easily an adaptive secure signature scheme. This is pretty cool. The testament that the original construction was pretty solid. What you need to add is an online extractable proof of knowledge to prove that you're really doing stuff correctly when you're following the diagonal line for the commitment step. And the reason because you need online extractability is so that you don't need to rewind for extracting the randomness the adversary used, so that you can achieve parallel composition pretty easily, because you never need to rewind. That's the whole idea, basically. But anyway, so this is the first result, but now, as I said to you, okay, by moving to chain GAIP, I obtain a security loss that is proportional to the number of elements that are in the chain. And unfortunately, our secret sharing the bad idea to be T over N share of the secret key. So what happens is, okay, I have an adaptive secure adversary, adaptive secure protocol, but the security loss is T over N. And in general, this is a pretty standard result. You can turn any static secure threshold signature in an adaptive secure one by adding a T over N security loss. That is, you are guessing your set of party the adversary will corrupt beforehand. So like our construction was basically pointless, but it was not pointless because like we are using a trivial result. It was pointless because there is too much share in the secret key. So there is still hope that we can lower this bound by simply exploiting a better secret sharing. And this is okay. This is the problem. And as I said, the reducing the number of elements in the secret key was also pretty important because otherwise it became impractical very quickly. So there were two reasons to improve the secret sharing. And this is the second solution. I called it less bad because it's still exponential, so it's still not great, of course. But from like a practical standpoint, it increased the range of applicability of our result by quite a lot. I will show you a couple of graphs later. And the idea, this is like a pretty agnostic result. You can apply it to any secret sharing you want, so as long as you're working in group. So what you do is simply, the idea is you split your size of part in half, that are P left and P right of size n over 2, and then you split also your secret in half by computing G as G1 times G2, and then you do a secret sharing with like a mobile threshold on the left and on the right of respectively G1 and G2 until you find either that the threshold is 1 or n. In such a case, well, you either do a normal secret sharing or like you simply give what you are sharing. By doing this way, you obtain many interesting property. So the first one is that you're reducing the number of share quite drastically. This is an upper bound. In practice, if I remember correctly, UB is the most common upper bound of the number of share, at least when the number grows. So we are still in an exponential territory, but this is the numerical result with the, I think it's orange, probably it's red, I don't remember. Dot are the normal secret sharing with the replicated one, where the blue one is the new improved version. So as you can see, like they are much lower, even if like they grow pretty quickly, but the range of applicability is way better. On the second hand, and this is pretty important, the communication round are always T. So you are not like having, in the previous case, you have like an exponential number of communication round. Now you have a constant number of communication rounds. So this is way better. Even if like the memory improvement is like lower, the time improvement is way bigger. And finally, you have a non-trivial security loss for adaptive security. So this is, of course, a nice result. Is this possible? Is it possible to do any better? Maybe yes, maybe no. Like this is still an open problem, and the idea is like, okay, there are many ways to improve the secret sharing, but as now the only way we found, like we are studying, is now we probably need to stop going with black box approach and introducing like studied approach with like structure and similar stuff as they do in isogenies and so on, because they can use a better secret sharing, but they also like relying on the group structure. So that's it. That is like the following process we are going to do. If you have any question, thank you for the attention.
So any question for Michelle? Yes, please.
Yeah, thank you for your talk. A question, if you would now instantiate your scheme with a concrete group action borrowed from some standard signature scheme, could you just inherit the security parameters, or do you need to adapt the security of the group action in this scenario?
Well, of course, every group action has its own security parameter. So like this is a framework where you can instantiate your group action, follow this structure, and obtain a secure signature. But then like the correct parameter, for example, your codes, need to rely on how hard is solving like the linear code equivalence. So like you need code with some properties or some other properties for other group action and so on. So determine like the exact number. Of course, you rely to like the best attack for your group action, because like at the basis there is like you need that your group action must have like lambda bit of security, and so like you like tailor your scheme and so on with that in mind. Yes.
Thank you.
Other question from audience? So maybe let's thank Michel again. Thank you very much.
Okay.